In this lecture video, we're going to look at a few probability distributions that come up in the context of certain applications because these end up being the sampling distributions of certain statistics. The first distribution we're going to look at is called the chi-square distribution. And so let y be a continuous random variable with PDF given by the following expression. So we see that it has a sample space consisting of the positive real numbers, and it takes on a value 0 otherwise. For positive values of y, the PDF is equal to y raised to the power k over 2 minus 1 times the exponential function evaluated at negative y over 2, all of that divided by the gamma function evaluated at k over 2 times 2 raised to the k over 2 power. So if a random variable, a continuous random variable, has this PDF, then it's said to have a chi-square distribution with parameter k. Now the parameter k is called the degrees of freedom associated with the distribution. Now to indicate that y has this distribution, we could write down the PDF, but we'll typically use our notation, abbreviated notation that we have been using. So we would use the tilde to denote or abbreviate the phrase is distributed as. And so we would say that y is distributed as a chi-square random variable with k degrees of freedom. I know my writing is kind of hard to interpret here, or hard to read, but this is a Greek letter chi, so chi squared. And then the argument here, this is the parameter k, the degrees of freedom associated with the distribution. Now you probably recognize that PDF as that of a gamma distribution with parameters alpha equal to k over 2 and beta equal to 2. And so if we go back and look at this, we see that this is the same functional form as that of the gamma PDF. And for alpha, we have k over 2 in this location and in this location, as well as in this location. And then for beta, we have 2. And so we see that this is that the chi-square distribution with k degrees of freedom is the same as a gamma distribution with parameters alpha equal to k over 2 and beta equal to 2. So the chi-square distribution is a special case of the gamma distribution. Now, because of that, we can immediately write down the moment generating function for the chi-square distribution with k degrees of freedom. It's equal to this expression, 1 over 1 minus 2 times t, all raised to the k over 2 power. Now, we can also use what we know about the mean and variance of the gamma distribution to determine the mean and variance of the chi-square distribution. In particular, for a chi-square distribution with k degrees of freedom, the expected value of that type of random variable is k, the degrees of freedom, and the variance of that random variable is 2 times k, or 2 times the degrees of freedom. Now, let's look at some results involving this kind of a distribution, this kind of a random variable. Let y1, y2, and so forth up to y sub n be independent and identically distributed. I'm sorry, they're not identically distributed. They are independent, but y sub I has a chi-square distribution with degrees of freedom equal to k sub I. And so the degrees of freedom are allowed to be different across these random variables. And so we will denote the degrees of freedom of y sub I by k sub I. Now with that, then it turns out that we know that the moment generating function of y sub I, which is the ith observation in the sample, that is equal to 1 over 1 minus 2 times t, all raised to the k sub I over 2 power. And so this is going to be the case I going from 1 to n. And so we see that the moment generating function depends on the degrees of freedom, all right? And these degrees of freedom, again, are allowed to vary. Now, let's consider the sum of these random variables. So we're going to be adding up these independent chi-square random variables. And so the question is, what kind of a distribution does this new random variable have? because the y's are random variables, the sum is a random variable as well. And so we want to know what kind of a distribution does the sum of independent chi-square random variables have. So the moment generating function of the sum of the y's using properties of moment generating functions can be derived. All right, so the moment generating function for the sum of the y's is equal to 1 over 1 minus 2 times t, all raised to the sum of the k's over 2. Now, the sum of the k's, the sum of the k sub i's, that is the sum of the degrees of freedom associated with the individual random variables. And so we see here, well, and by the way, we recognize this as the moment generating function of a chi-square distribution with degrees of freedom equal to the sum of the degrees of freedom of the individual random variables. Okay, and so we see that when we start off with independent random variables, then if we all from chi-square distributions, but again we're allowing the degrees of freedom to vary, then the sum of those independent chi-square random variables is also a chi-square random variable, the degrees of freedom of which is the sum of the individual degrees of freedom. Now, as a special case, let's suppose that these y's, y1 through y sub n, are independent chi-square random variables with 1 degree of freedom. So not only are they independent, but they all have the same chi-square distribution, the chi-square distribution with 1 degree of freedom. So they are in fact independent and identically distributed. Then from this previous result, it follows then that the sum of the y's has a chi-square distribution with n degrees of freedom. So that can be helpful. That can be a helpful result to know in certain theoretical situations where we're trying to find the distribution of some particular random variables. And we may have an opportunity to look at this in subsequent lectures. Okay, so just kind of a review here. The chi-square distribution with k degrees of freedom is the same as this is equal in distribution here. So that's the same distribution as the gamma distribution with alpha equal to k over 2 and beta equal to 2. Okay, now just to finish this particular section out, and this is where the chi-square distribution comes into play. All right, we said that we're looking at a few probability distributions here that show up in the context of applied situations in the sense that these random or these distributions are the sampling distributions of certain random variables associated with the sampling process. And so let's suppose that we have a random sample from a normal distribution with mean mu and variance sigma squared. All right, so these are the x1 through xn are independent and identically distributed, or IID. And let's let s squared be the usual sample variance, the sample variance that we learned about in our first methods class, the version with n minus 1 in the denominator. You'll remember that the sample variance, so well, really any variance, whether we're talking about a population variance or a sample variance, when we talk about variance in general, we can describe it as the average squared deviation about the mean. And so when we're talking about a sample variance, we're talking about the average squared deviation about the sample mean. And so anyway, it can be shown, and this is where the chi-square distribution comes into play. It can be shown that if we take the sample variance and clear the fraction by multiplying by n minus 1, and then dividing that by the population variance, the variance of the population we're sampling from, that random variable right there, n minus 1 times s squared over sigma squared, has a chi-square distribution with n minus 1 degrees of freedom. And so we can use this as the basis of constructing hypothesis tests and also constructing confidence intervals for the variance sigma squared of the population that we're sampling from. And so before we get into that section, and that's the next section we're going to get into in looking at inferences for single populations. Before we really get into that, that's why I wanted to look at this particular set of notes and introduce you to the actual functional representation of the chi-square distribution. And now that we've seen the chi-square distribution, we can talk about students' t-distribution as well. So let's let z and v be independent random variables, where the random variable z has a standard normal distribution. That is a normal distribution with mean 0 and variance 1, and therefore standard deviation 1. And let's let the random variable v have a chi-square distribution with k degrees of freedom. So this is the distribution we just looked at. And this is another reason why we had to look at the chi-square distribution first. So we have a standard normal random variable, we have a chi-square random variable with k degrees of freedom, and we're assuming here that z and v are stochastically independent. Now let's take those two random variables and define a new random variable. We're going to call it t, and it's defined to be z, the standard normal random variable, over the square root of v divided by its degrees of freedom. So when we do that, the resulting random variable t has what's called a student's t-distribution with k degrees of freedom. And you'll notice that the number of degrees of freedom associated with the distribution of t is the same as the number of degrees of freedom that are associated with the chi-square random variable that is in the denominator of that random variable. Now, the PDF of the t-distribution with k degrees of freedom is somewhat complicated because it involves the gamma function in a couple places. So we see that, oh, and by the way, let me just say that this distribution has a sample space equal to the entire real line, and that should be obvious because we know that the numerator of the t random variable, which is the standard normal random variable, it has a sample space which is the entire real line as well. On the other hand, v has a sample space that consists of the positive part of the real line, and so it's always going to take on a positive value, and so we can take the square root of that without any problem, and the denominator of this random variable t is therefore positive. It's always going to be positive. And so we can see that this random variable can take on any real number in the real line. Now, the PDF of the t-distribution with k degrees of freedom is equal to the gamma function evaluated at k plus 1 over 2 divided by the square root of pi times k times the gamma function evaluated at k over 2. All of that times the expression 1 plus t squared over k raised to the negative k plus 1 over 2 power. Now, this is, we can write it down fairly succinctly, but only because we're using the gamma function, which we know is actually is an integral expression. Okay, so this function would, in general, be difficult for us to integrate and things like that. But we're not going to have to do that. We're going to let the computer do all that kind of calculating for us if we need that. Really what we would need to do that for is to compute the CDF of the t-distribution, but we have t-tables for that. If you've got a TI-84 calculator, and I believe a TI-36X Pro will do the same, they typically, many of the calculators these days typically have students' t-distribution, the CDF of that distribution built in to the calculator, and probably the PDF as well. Now, I would note that if you plug in negative t for t, then you see here that the only place t shows up is right there. And so if you plug in negative t, you're going to have negative t quantity squared. That's going to be the same as t squared. And so you can see here that the PDF evaluated at negative t is equal to the PDF evaluated at t. And so what this implies then is that this PDF, the PDF of the t-distribution with k degrees of freedom, is symmetric about the t equal to 0. Now, let's let x1 through xn be a random sample from the normal distribution with mean mu and variance sigma squared. And let's let x bar be the sample mean, and we'll let s squared be the usual sample variance, the sample variance that has n minus 1 in the denominator. Now, in our discussion in the module back on sampling distributions, we showed that when we're sampling from a normal distribution with mean mu and variance sigma squared, that the sample mean is also normally distributed with mean equal to mu, the mean of the population we're sampling from, and with variance equal to sigma squared over n. All right, and so if we standardize x bar by subtracting off the mean of its sampling distribution and dividing by the square root of its variance, okay, so that's what we're doing here, then the resulting random variable has a standard normal distribution. Now, in talking about the chi-square distribution just a while ago, we pointed out that when we're sampling from a normal distribution, if we calculate the sample variance, if we multiply that by n minus 1 and divide by sigma squared, then that resulting random variable has a chi-square distribution with n minus 1 degrees of freedom. Now, it can be shown, we're not going to prove this, but it can be shown that since we're sampling from a normal distribution, the sample mean and the sample variance are stochastically independent. So let me just again emphasize the fact that the assumption here is that we're sampling from a normal distribution. Okay, and so when that's the case, the sample mean and the sample variance are stochastically independent. And so that implies that the standardized version of x bar, all right, x bar minus mu over the square root of sigma squared over n, and also n minus 1 times s squared over sigma squared, those two random variables are stochastically independent as well. Okay, so now let's apply what we know about the t distribution and how to construct a t distribution or a t random variable. So you'll remember that if we can obtain a random variable that has students t distribution, if we take a standard normal random variable and divide it by the square root of a chi-square random variable over its degrees of freedom. So that is what I'm doing here. This random variable here in the numerator has a standard normal distribution. Here's my division bar. And then in the denominator, I have the square root of a chi-square random variable that has n minus 1 degrees of freedom, and I'm dividing that by the degrees of freedom. And so by definition, we know that that random variable has a t distribution with n minus 1 degrees of freedom. But now notice that we can simplify this. Notice that we have in the denominator here underneath the square root sign, we have an n minus 1 here in the numerator, and I've got an n minus 1 in the denominator. So that n minus 1 cancels with that n minus 1. Then, and this may be harder to see, but we have a sigma squared underneath the square root sign here and a sigma squared underneath this square root sign. We're going to be able to cancel those out. And so what we're left with is this expression here. If you do the cancellation correctly, what you get, t being equal to x bar minus mu over the square root of s squared over n. And we could also obviously write that as x bar minus mu over the sample standard deviation over the square root of the sample size. Now it looks like all we did was replace, it looks like all we did here, in getting this down here, it looks like all we did was replace sigma squared by s squared. But you can see that the way we got there is a little bit more complicated. But that's effectively what we're doing. We're effectively just replacing sigma squared with the sample variance s squared. And so what we know about this random variable, this random variable has a student's t-distribution with n minus 1 degrees of freedom. So let me go back up here. If we standardize x bar by subtracting off the mean of its sampling distribution and then dividing by its standard error, that random variable has a standard normal distribution. But if we don't know sigma squared, and so we plug in s squared, an estimate of sigma squared instead, that random variable no longer has a standard normal distribution. It has a t-distribution with n minus 1 degrees of freedom. And so if you think back to or think about a t-test and confidence intervals that you construct using a s squared, the estimate of the population variance. We said in those notes that the resulting random variable has students' t-distribution with n minus 1 degrees of freedom. And this is the theoretical justification for that. Okay, so we've looked at two distributions that show up in the context of sampling and developing methodologies because they are the sampling distributions of certain statistics that we calculate in performing hypothesis tests or constructing confidence intervals. So we've looked at the chi-square distribution. We've looked at the t-distribution. There is one other distribution that we're going to look at, but I'm going to hold off on looking at that until we get to the point in the notes where we are going to start using it. And so I will cover that particular distribution, the F distribution, when we need it. And so that wraps up this lecture video. We'll continue on with the next topic in the next lecture video.